Here we investigate the formation of manganese which occur in vein networks typically in sandstones and quartzites of the Cape Supergroup. We use the Montreux Reserve as a case study site where mining has previously taken place, though typically of quite small deposits with phosphorus concentrations that render the manganese no good for steel making. So today we're in the Montreux Nature Reserve up behind Franschhoek. There's some spectacular snow in the background. I hope you can see it behind my big head. But what we're really here for today is to investigate the controls of the mineralization of manganese that we find in this area. So we're going to look at some field outcrops. We want to think about these things in terms of a source transport trap model. That is to say, what is the source of the metals? What is the source of the fluids that then transport those metals? How does it transport through some sort of structural conduit? And then finally, how do we find a nicely constrained trap site which can precipitate these manganese minerals in a high enough concentration to make it mineable? This schematic gives an overview of how that source transport trap model may work for the Cape manganese. Briefly, the source of the fluids would be from rainwater which percolates downwards through the soil profile and into the fracture networks in the highly fractured sandstones of the Cape Supergroup. The source of the manganese can be background concentrations that come both from the soil profile as well as from the surrounding rock mass. That water, which we call meteoric water, has the potential to pick up manganese from the surrounding soils and rocks and transport it through these fracture networks, which are highly prevalent in the quartzite units. Manganese transport is facilitated and higher solubilities can be achieved if that water is warmed, like in a hot spring, or if there are high chloride concentrations associated with the fluid. Finally, for the trapping mechanism, this is achieved when those manganese-rich fluids move out of the fracture networks and become re-exposed to the atmosphere. Here, a chemical reaction between oxygen from the atmosphere and the manganese gives rise to the precipitation of manganese minerals like pyrolusite, cryptomelan and cyanomelan. And then following a long strike of the main mineralization, they've really taken out the high-grade stuff. Grades here probably on the order around 35% manganese, which is nowhere near as high as what we see in the Kalahari manganese fields. And again, that issue of the phosphorus coming in. If you've enjoyed this video, and importantly, if you've learned something from it, like it, share it, and then remember to come study earth sciences at Stellenbosch University.